There guys, Mr. Carlson here. Let's talk about something that's a lot of fun. It's molar mass of a gas. That's how you know that what we're talking about today is fun, because it actually rhymes. The molar mass of a gas. Now, when we're talking about the molar mass, let's remind ourselves exactly what we are talking about. That's, remember, molar mass is equal to the grams per mole of something. So typically, right, what we do is if we need to find the molar mass of something like H2O, if I want to know the molar mass, I take the mass of 2 hydrogens from the periodic table, I add it to the mass of 1 oxygen, and that would be the grams per mole of that. So that's what we're going to talk about today, is how do we actually determine this? How do we determine this? Let's say if we have like an unknown gas, like we didn't know what it was, but we knew like the pressure and the temperature of that gas, we could actually determine what its molar mass is, and then from there determine what the gas is. So for the molar mass of a gas, there's actually an equation that we get from this when we relate pressure, temperature, and volume to the amount of moles of something. And this is the equation that we get from it. Molar mass is equal to the density of the gas times our gas constant times the temperature of the gas divided by the pressure of the gas. So the density of the gas is what we would need to know in this case, the density of the gas. Remember that density, by the way, just in case you forgot, density is equal to grams per, actually no, you know what we're going to say, because I'm not going to say it, I'm not going to put the units, we're going to put mass over volume, because our mass and our volume units will change. So I'm not going to put grams per milliliter or grams per centimeter cubed, because that will change, but it's mass over volume. Mass over volume is what our density is. So again, those units could change. It could be like grams per liter, kilograms per liter, depending on what we measure the mass or what we measure the volume in. So we've got to be careful of that. But anyways, so what this is showing us that is I can determine the molar mass of a gas if I know the density of it and I know the temperature and pressure that it is at. So in fact, let's write that down over here. If density, whoops, froze up on me, of a gas at a given pressure and temperature is known, then the molar mass can be calculated. So let's take a look at a simple example of this right off the bat. Let's say that the density of a gas was measured at 1.5 atmospheres and 27 degrees Celsius, and it was found to have a density of 1.95 grams per liter. Let's calculate the molar mass of that, shall we? So let's write down what we know. We know that the pressure of this was measured at 1.50 atmospheres. Our temperature is 27 degrees Celsius, but remember, we're going to add that to 273, because let's make another reminder here that when we are using our portions of our ideal gas law, we are going to want to have pressure in atmospheres. We're going to want to have temperature in Kelvin. So let's come back down here. Our pressure is already in atmospheres. Our temperature now needs to get in Kelvin just by adding 273, which is going to give us 300 K. We also have the density of the gas. They tell us is 1.95 grams per liter. Okay, so all I have to do in this one is just plug in our numbers into our equation that we've got up here. Again, molar mass is equal to dRT over P. So let's rewrite that down here. So density times our gas constant. Actually, you know what I'm going to do right now? Let's do this. Let me back up a little bit. Let's write out this equation. What we're going to do is we're going to include our units with all the numbers, which is a habit that we are not in right now, but we should get into the habit of doing that, of writing out our units that we have for each number and see how they cancel out to give us our units, the units that we're looking for. So remember, our units for molar mass in the end, molar mass is grams per mole. So let's see if when we put all these in, we do the math, let's make sure that our units cancel out to give us this unit of grams per mole. So we've got the density, which is 1.95. Units for that are grams per liter, okay, times our gas constant, which you probably don't remember the units for that. 8206 is the our gas constant. Now the units for that, you probably don't remember this, but are liters times atmospheres over K times moles. That's a big unit there. So liters times atmospheres over K per mole. Basically our volume times pressure, and our temperature times the number of particles is our gas constant, the units for our gas constant. And then times, what was our third thing here? Temperature, right? So 300. Unit for that is Kelvin. All over the pressure, 1.50, which is measured in atmospheres. So now let's take a look at this before we just start plugging in numbers and randomly calculating things without looking at the units. If I look at what cancels out here, let's take a look at this temperature, for example. I've got K here, and then I've got K on the bottom of this. So when I multiply these two numbers through, since this is on the bottom here, and this would be on the top, or the numerator, that means that this K and this K are going to cancel each other out. So it's whenever we're dividing the same units, right? Whenever we divide the same units, they're going to cancel each other out. Just like I've got atmospheres up here, I've got atmospheres down here. So when I plug those numbers in and I calculate them through, they're going to cancel each other out. So I'm just going to cancel them off right now before I even calculate anything. And then also, if I look, I have liters here on the numerator. I've got liters here in the denominator. And so again, when they divide each other, they are going to cancel each other out. And now notice what I'm left with. Grams in the numerator, moles in the denominator. So when I, again, do this math through here, I'm going to be left with grams per mole, which is what I want to be left with because that's the units for molar mass. So let's actually plug these numbers into the calculator and determine what we get. What do we get? We get 32 grams per mole. That is the molar mass of this unknown gas that we have. All right, so that's a pretty simple example there. Now, like always, let's do a very cumbersome, long, and difficult problem. Okay, let's take a look at this one. Let's say that we've got a compound that has an empirical formula, CHCl. We have a 256 milliliter flask that's at 373 K and 750 torr. And it contains 0.8 grams of this gaseous compound. What is the molecular formula? So for this problem, we actually kind of have to go back to a unit from the beginning of the year in which we were determining empirical and molecular formulas, which I bet you definitely remember how to do that. Remember that we can have, for a molecular formula, it's basically just changing the amount of what we have in the empirical formula. So the empirical formula is the lowest ratio, which in this case is just 1 to 1 to 1, right? One molecule of carbon for every one of hydrogen for every one of chlorine. That's the empiric. That's the lowest ratio I have. But I can have different molecules with different formulas. So in other words, I could have C3H3Cl3 or C6H6Cl6. And those could be different molecular formulas for this. So what this problem wants us to do is figure out what's the molecular formula if I know that I'm starting with this empirical formula, and I've got 0.8 grams of this in 256 milliliter flask at this temperature and pressure. Can I figure out what is the molecular formula of this gas? So there's a lot of steps here. Let's just first remember this, that if I want to figure out the molecular formula, let's think back. How do I determine that? Well, what we had to do is we need to know the mass of this compound, of this molecular compound. I need to take the molar mass of this compound, and I need to divide it by the molar mass of its empirical formula. The molar mass of the empirical formula. Because if I do that, then that's going to give me a factor by which I can multiply these by. So I might divide these, and it might give me a factor of 5, let's say. And so then I know that I need to multiply each one of these by 5 to figure out what my molecular formula is. Hopefully this is ringing some bells. So what I need first is I need to know the molar mass of this unknown gaseous compound, and I need to know the molar mass of the empirical formula. That's what I need to figure out in order to answer this question. Well, it's easy to figure out the molar mass of the empirical formula. All I have to do is take 1 carbon added with 1 hydrogen added with 1 chlorine, and that will give me the molar mass of the empirical formula. But how am I going to figure out the molar mass of this of the molecular compound, right? How am I going to figure out that? Well, good thing we just learned up here that we can figure out the molar mass by using parts of our ideal gas law, right? So let's bring this down here. So I'm going to need to use this equation of molar mass is equal to density times our gas constant times the temperature all over the pressure. Okay, so I know parts of this. I know the temperature is 373 K. I know that, well, the gas constant is just a constant, always the same. I know the pressure, 750 torr. And do I know the density? Well, the problem says that this is a 256 milliliter flask. 256 milliliter flask. And it contains 0.8 grams. Well, that's a density right there, right? Because remember that density is mass over volume. Here's a mass, here's a volume. So therefore, I know what the density is. I'm just going to take that number, 0.8 grams, divided by the volume. Now, what I'm going to do, though, is I'm going to convert this right away into liters. It's in milliliters, but I'm going to convert it to liters. And the reason why I'm going to do that, let's go back up here. Remember with our units up here, with this universal gas constant, remember this has units of liters. Units of liters. We want to have things in liters, atmospheres, and Kelvin for when we're using this. So I'm going to make sure I convert that into liters for things to cancel out correctly. So let's come back down here. 0.8 grams per, so I'm just going to move this decimal over 3 places, 1, 2, 3, over 0.256 liters. So let's punch that in the calculator. 0.8 divided by 0.256. So our density here is 3.125 grams per liter. Grams per liter. All right. Now I know everything else. Let's plug this into the equation and see what we get. So, equals, density is 3.125 grams per liter times our gas constant, which is 0.08206 liters times atmospheres over K times moles, times our temperature, which is already in K for us, or in Kelvin, so I don't have to do any conversions there, 373 K, all over our pressure. They give us the pressure in torr, so we're going to have to convert that into atmospheres. So 750 times, there is 760 torr for every 1 atmosphere. So I'm just going to do that calculation right away. Let's see, what does that give us? 750 divided by 760 gives us 0.987 atmospheres. So I'm just going to get rid of that right now, actually, before I do anything else. All right, so now I've got everything I need. Let's punch everything in to see what we get. So 3.125 times 0.08206 times 373. So up in the top here, I get 95.65 all over 0.987. Divide that out, 0.987, and I get 96.9. And again, we've already talked about this up there, but so liters goes away, atmospheres goes away, Kelvin goes away, so grams per mole. Now, I'm not done with the problem. This is the molar mass of this unknown gas here. Okay? But the problem wants us to figure out the molecular formula, and so what I need to do is I need to take the molar mass of the formula and I need to divide it by the molar mass of the empirical formula to figure out what the molecular formula is. So let's keep going with this. Let's come down here. Oh, whoops. Forgot to erase this. That was the final answer from before. So what we're going to have to do, first we're going to have to figure out what is the the empirical formula mass. So I've got CHCl, one of each. So the empirical mass, so we'll say empirical mass is equal to, let's see, carbon is 12. We'll just round it. We'll say 12 plus 1 hydrogen plus 35, what is it, 0.45 I think for chlorine. So we'll say 35.45 plus 12 plus 1. So we get 48.45. So this is grams per mole. That's the mass of our empirical formula. So all I have to do is take this divided by that. 96.9 divided by 48.45. And again, what this is going to give us is a factor. 96.9 divided by 48.45. Factor of 2. That means I have to multiply my empirical formula by 2. Therefore, the molecular formula is C2H2Cl2. There is my final answer. There's the molecular formula for that one. So I know that that one is kind of a little more long and complicated of a problem, but again, it's still the same. You're still using the same basic principles that we've learned. It's just that we have to go back and kind of remember some things that we've learned from before.